In item 4, we're asked to take a look at a building column that has up at the top level 115 kips, at the next level down 155 kips. So pretty big forces on a W10 by 60 column. There's our cross-sectional area and the amount of steel that we've got, or rather, I'm sorry, the largest elasticity of the steel, should we need to have it. And we're supposed to figure out how much this top of the steel column is going to displace. And clearly here it's going to displace downwards, and that delta C at the top then is going to be comprised of the shortening that happens in the segment from C to B plus the portion that happens from A to B. So it's composed of both of those. In each case, those are going to be equal to the axial force times the length over AE of that segment. The E and the A are going to be the same for this column, but the N and the L's will not be as we walk down. Right? This might be even more easily characterized as N of that second story over the axial stiffness of that second story plus the N over, N2 over K2 and N1 over K1, where K2 is EA over L of that second story, which is the BC segment. Right? So that'd be 29,000 kips per square inch times our cross-sectional area, 17.6 square inches, over the length, 14 feet, times 12 inches. And that will equal about 3,038. Oh, that's the other one, sorry. That is 2658 kips per inch. It's going to be our first story. That's EA over L for AB is equal to 29,000 times 17.6 over the 16 times 12. I think I got these all messed up. Let's make sure I've got this right. First story, 16 feet, that's times the 12. I had it right the first time. Only thought I was wrong, right? So that's the one that's equal to 2658. The other one must have been right at 39 or 38, but we'll check again. So that was right the first time. Okay, so that means that we just have to figure out what our axial force is, and of course it's very easy. Up in this top, we only have the 115 there, and then the axial force below it's got to be 115, and then down below, well, we've got now the whole column tree, so we've got two axial forces, or rather applied forces, 115, 155, and the resistance to that then has got to be 270. Right, so that means our delta C is going to be equal to 115 kips over our 38 kips per inch up in that upper story, plus 270 kips over our 2658 kips per inch. Right? Notice all the units are going to work out. Right? The stiffness, kip over inch squared times inch squared was now kips. Kip over inch, that was what we had here. Now kip over inch is going to give us inch. So let's just bang it out. 115 divided by 38 plus 270, 2658, and that equals 0.1394 inches. And so our answer then at the bottom, 0.1394 inches acting downwards. An absurd level precision, and also for a very tiny amount Not actually at all surprising, about 1/8 of an inch for a column. And these are pretty heavy loads for a 2-story column situation.